Hey everyone, in this tutorial I'm going to do the midterm review. I invited Apurva from Brown University and Subarna from New York University to help me make this tutorial. You're going to discover lots of things in this tutorial, but we're going to mention three. I'll mention one, Apurva going to mention one, Subarna going to mention one. Kinetic energy, right, is equal to work, but be careful. Kinetic energy is half mv squared, which will not match with all type of works, because as you see in this problem there are 5 types of work, right? Work done by x, work done by y, work done by normal, work done by f, work done by g. They will not match with kinetic energy. Kinetic energy only match with
the total work,
the network.
Another thing you need to watch out for is that the force needed to accelerate the object is not the same as the force needed to move it with constant velocity. The reason why is because there's two different kinds of friction: static friction and kinetic friction. So make sure you're aware of that. One last confusing thing that I think is nice to learn from this tutorial is that there's a difference between, well, power, average power, and instantaneous power. It's an instantaneous quantity too, because if you rearrange the terms in the equation, you can write it as force multiplied by velocity, which are both two instantaneous quantities on their own, but you can also take the averages of those. Before this, it's very easy to think that, well, power is just an average term, something that you can only apply to an interval of time, but now you can actually see how much power is being done at any point.
10 kilogram box, right? Sitting on the surface with friction is mu k 0.1 and mu s 0.2. So far so good. You apply 100 Newton at 30 degree. This is time 0, displacement 0, velocity 0, acceleration f net, fs, fk, power, work, kinetic energy. The box is moving for 10 meters, so that means displacement is 10. Is that right? You have to find velocity, final acceleration, and then f net, and then fs, fk, work done by x, work done by y, work done by n for normal force, work done by g, work done by fk, and network. Is that too much?
Network in which direction?
Total network, of course, at the x direction.
Well, yeah.
Network is x direction.
I would say it's too much, but who cares? Half of them are zero anyway.
Zero saves lives. Did I not tell you before? Thanks to Bihar, Brahma Gupta. Okay, so over here, kinetic energy, right? Is there anything we need to do? Okay, power. And then what? Minimum force need to accelerate the object, and minimum force to what?
Constant velocity.
To move the object constant velocity. Okay.
Horizontal direction, we have the force of friction from the ground that is pulling it in the opposite direction. Static or kinetic?
Hey,
we'll find out. So FA is 100 newtons, but in the horizontal direction, which is the only one we care about, it's 50 rad 3.
Just write 87. You have a calculator.
How do you expect me to know that without calculating it first?
I gave you a calculator.
I'll calculate it. Give me some time.
Okay.
So FA is 50 rad 3, which if you put it into the calculator, I know it's 86.6. Is 87 newtons. And then upward, we have this force of 50 newtons, which initially seems to not be that important, but then you realize that, well, the force of friction is actually dependent on the normal force, the amount of work the ground has to do to keep the block standing here and not, fall through the floor. So what is this normal force? Well, normally it would be the exact same as the force of gravity, which is m times g. In this case, g is 10. So Fg is 100 newtons. And so the normal force would be 100, but since this force is already supporting it, it only has to be 50 in order to keep the box stable. And now finally we have Ff, which is just mu Fn. Now the thing is, mu Fn means that the maximum static friction is 0.2 times 50, which is 10 newtons. But of course, the applied force in the horizontal direction massively outscales both that and the maximum kinetic friction, which means that it has to be FFK, not FFS. And FFK is going to be half FFS because the coefficient is halved. So FFK is 5 newtons in this direction.
Okay, thank you. Save the space. I'm going to put it over there. This one is what? 100 Newton. And this one is Fg. This one is Fx. Fx is how much? 87 Newton. This one is what? Fy. Fy is 50 Newton. And this one is Fn. Fn is how much? 50 Newton. And this one is Fk. Fk is how much? 5 Newton. Direction will be the horizontal force Fx minus the kinetic friction. So Fx is 87. The kinetic friction is 5 newtons. So the net horizontal force is 82 newtons. Okay, and net force in the y direction. There is no net force in the y direction. Yeah, because the box is up. Yeah. So find the acceleration. Everything okay. What we wrote. Yeah. The x direction. That's right. So the mass of the box is 10. So that means the acceleration is 82 over 10, which is 8.2. The net force 82 Newton. Is that right? Yes. And acceleration 8.2 meter per second. Is that right? So Fs, assume that it was unmoving. Okay. Fs is, what is Fs max? Well, max. Is 10 Newton is because 0.2 times 50, which is 10 Newton. Okay. 10 Newton. Why the object is moving? Because 87 Newton is bigger than 10 Newton. So object is moving. So this diagram is correct. Okay. Fk is 5 Newton. Why is that? Fk is mu k Fn. Is that right? So mu k is how much? 0.1 times 50, which is 5 Newton. Okay. 5 Newton. I want you to find the, power over here is 0. Why is that? Yeah, and kinetic energy over here is 0.
So we can just use d is equal to half at squared, and then we have t squared is equal to 2d over a. So t is the square root of 2d over a, which is the square root of, well, 20 over 8.2, or 1.56 seconds.
Update the table.
Okay, sure. And the velocity is, well, there's no initial velocity, it's just acceleration times the time, which is 8.2 times 1.56, or about 12.8. Is 82. The static friction is the exact same. The kinetic friction is the exact same.
Power is work over time. Okay. That power is not work over time. Oh, okay. Then we can use FV. This is instantaneous power. Okay. We know the force in the x direction is 87.
No, it's 82.
No, it's 87.
You forgot the force.
Oh, I see. That's right. Thank you. So this is 82 newtons, and the horizontal velocity is 12.8. So that is, let's see, 82 times 12.8, 1050 watts. Okay. 1, 2, 3, 4, 5, 6. I'm gonna in fact draw the box for you. So in the work equation, there are how many physical quantities? 2, F and D. Okay, so two physical quantities involved with work. So the force, when force act at the direction of the displacement, work being done. Okay, which one is constant between these two physical quantity? No, d. D is constant. So what does that mean? D is 10, 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 and D is 10. So D is constant for all 6 problems. Okay. So you're changing the force. Of course. Because not all force do the same amount of work. Okay. All right. So we're done with this one. Now we're gonna do the first one. I'll do this one. This one WX. I see WX and I see 87. Okay. I'm gonna go over there and I'm gonna write FX. Okay. Then I'm gonna write work is F. These two are parallel, right? So I'm gonna write D. That's it, right? Can you follow? So you're gonna do the everything else same way. Parallel D, right? So now instead of parallel, what I'm gonna write? FD cosine theta, right? Okay. So now I'm gonna write DF cosine theta. So D is 10. F cosine theta is how much? 87. So this is how much? 870. Okay, so I did this one 870. Can you do this one the same way, Jule?
Force is in the y direction. So Fy is 50 newtons. This is Fy. Okay. So that means that there is no horizontal component of the force. So F is let me first write F parallel D. Okay. So F has no parallel component. So it doesn't matter that D is 10. The total work in the y will be 0. So this will be 0 joules.
Isaac, next one.
So
Is 50 newtons in this direction. Unfortunately, the displacement is exactly orthogonal to it, which means, you know, it didn't do crap. The normal force is 0 joules because cosine of pi over 2 is 0. Do I have to do all of them?
Yeah, do them. They are the same.
Well, the work done by gravity, it's also vertical, even if it's in the opposite direction. Cosine of minus pi over 2 is still 0. So the work done by gravity is 0. For number 5, we have the work done by static friction. If the static friction existed, that would be 10 newtons in the exact opposite direction, which means that it would be doing negative work. So the work done by static friction would be negative 10 newtons times the distance traveled, which is 10 meters. So we have 10 joules. No, 100 joules. And finally, we have the work done by kinetic friction, which it's the same direction but half the magnitude because we have half the coefficient of friction, which means it's just going to be half the work.
Okay, Ralph, we're gonna find the net work.
net work in the x is work done in the x minus work done by kinetic friction. So this is 87 or 870 joules minus 50 joules. So that'll be 830 joules.
What?
Yeah.
20.
No.
20, baby.
Oh, sorry. 820.
Can we cut that out?
Hey,
Yeah.
it's not about the mistakes. It's about the
So
arithmetic.
no, that's not happen. It's a learning thing.
1/2 m
No, fast
V
iteration.
V squared.
It's the same.
You got 80.
No, it's not the same. You'll see that.
Sorry, man, but you got that wrong. It is the same by the work energy theorem. This is an approximation. That's why it's wrong.
Okay, so write 120 then.
There's a whole thing called the work energy theorem.
Right, so far so good? Okay, so fx has to be equal to fs. Okay, so fx is what? We're gonna write fx is 0.86 or 87f, and fs is, you're gonna write mu as fn, right? Let me see.
Oh, now I figured out the reason.
Okay,
Fn is
do it.
that the total force, Fa is equal to F, has two components, Fx, which is F root 3 over 2, and Fy, which is F over 2. And these ratios are because it's at a 30-degree angle. So now, what we have to do is make sure Fx is equal to Fs, but the problem is that Fs is dependent on Fy, because normally the normal force is equal to Fg, right? But here, since our applied force is taking some of the load off of whatever's holding up this block, that means Fn is going to be lower. It's going to be Fg minus Fy. So that means Fs is going to be mu s times, well, mg minus Fy, which is F over 2. That has to be equal to the force in the x direction, which is F root 3 over 2. So you get 0.2 times what's mg, 100, minus F over 2 has to be equal to F root 3 over 2. So if you bring all of the terms containing F to this side, we get F times the square root of 3 over 2 plus 0.1. Okay, so we have the square root of 3 over 2 plus 0.1, which is approximately 0.966. And so F is approximately 20 over 0.966, which is 20.7 Newton.
So we have fx. Oh wait, we don't know what fx is. We have to find the minimum. Okay, so this is okay, and we have force of friction. This is mu Fn. Okay, and Fn will be mg minus mu k. Yeah, okay, that's right. Yeah,
Equal to fx.
yeah. So these two will be the same. So this is 0.87 f.
Write 0.5 f on the in the bracket.
Right here. Okay. Okay, so now we just have to solve for f. So mu k is 0.1. Okay. M is 10. So this is 100 minus 0.5 f is 0.87 f. Okay. Let's see. I'm gonna divide both sides by 0.1. 0.87 over 0.1. So this is 8.7 f equals 100 minus 0.5 f. So 8.7 plus 0.5 is 9.2. Okay, so 9.2 f equals 100. So f should be 100 over 9.2, which is 10.8. Yeah. Okay.
So
FF versus FH trend looks like this. you go linearly in the beginning, you get the sudden drop because Fa reaches the threshold to break static friction, and then it stays the same because of kinetic friction. So now we just have to find what all of the numbers are. So here the number is 20.7 for acceleration.
So circle the 20.7 on the board.
Yeah, sure. And here the number is, well, the max static friction, 10 newtons. Then here the number is the max kinetic friction, 5 newtons. And, well, that's pretty much it.
Where is the 11 Newton?
Well, 11 newtons isn't going to do anything in the static friction region. And by the time we've reached the kinetic friction region, we're already past 11 newtons.
Okay. So how are you going to explain the audience?
I guess you can put 11 at the intersection of this kinetic friction line and here. So kind of like this.
Okay. What does that mean?
It essentially means, I guess,
It's easier to keep it moving.
Yeah, the problem with the number 11 is that this entire graph is modeled off of saying something like this. If I keep pushing it with more and more force every time, eventually it'll start moving, and here's how it will look. But the problem is, if you push it once with 11 newtons, that's not going to do anything. You have to start pushing it with enough force to break the hold, and then go to pushing it with 11 newtons. But that's not something this graph can really represent.
Very good. Raf, don't you think our teacher don't teach this way?
Yeah, this was nice. Actually, what was nice was the 5 different work,
Yeah, our teacher don't
like a
teach
little
this
box
way, no?
for each one. That was nice.
This is like summary of how many chapter? Like
Most of kinematics, I
Yeah.
think. Yeah.
yeah,
And
one
most
problem.
of dynamics,
And
probably.
this problem is doesn't look like a separate. It's like a
Yeah.
yeah,
It's one big problem.
yeah, it's like a branches of same tree.
Yeah. Yeah.
Okay.
Did you make this problem?
Yeah.
Or? Oh. Okay. Yeah. Okay. So what I was gonna say, this is very similar to riding a bike. You know, if you ride a bike, that it's much easier to keep the bike moving than to get the bike started. So same idea here. It's much easier to keep the box moving with only 11 newtons of force, and that's because the kinetic coefficient is half of the static coefficient. Same reason why the force needed to accelerate is almost double the force needed to move it at a constant velocity. Let's start with the easiest one, AT. So the acceleration is constant, 8.2. Okay. And it accelerates for 1.5 seconds. Okay. So if you have a constant acceleration, then you have a linear velocity, and the final velocity is 12.8 after 1.5 seconds. And if you have a linear velocity, then you have a quadratic displacement. And the final displacement is 10 meters after 1.5 seconds. 1.5. There we go. Now the force will look just like the acceleration graph multiplied by the mass. So the mass is 10. So that means the force will have to be 82 newtons constant for 1.5 seconds. Well, actually, wait, this is, yeah, I think that's right.
First of all, the force of friction is constant because the applied force doesn't change. It's always the kinetic friction, which is 5 newtons over the 1.5 second duration. Then we have kinetic energy, which is the next easiest. We know velocity is linear, and we also know kinetic energy is a constant multiplied by velocity squared, which means that if velocity is linear, then Ke has to be quadratic with time. So it has to look something like this, where it ends at 1.5. And over here, well, the final kinetic energy is 820 joules. And of course, by the work energy theorem, or just by basic kinematics, we have that work is the exact same as kinetic energy. So it also goes up quadratically over time, ending with 820 joules over 1.5 seconds. And now finally we have power, which we can represent by force, which is a constant, multiplied by velocity, which is linear, which means power is also going to be linear since it's directly proportional to velocity, giving it 1.5 here and 1050 here.
From kinematics to force to energy. The smooth transition from kinematics to force to energy. So these three things I want you to discover. We made this tutorial on Christmas Day to help you get 100 in the midterm. So good luck.
Good luck.